Welcome to the survey of the elementary principles in classical mechanics. Today we are going to continue discussing exercises, and we will begin with a problem involving momentum conservation in radioactive decays. The statement is as follows. A nucleus originally at rest decays radioactively by emitting an electron of momentum 1.73 MeV over c and, at right angles to the direction of the electron, an antineutrino of momentum 1 MeV over c. In what direction does the nucleus recoil? What is its momentum in MeV over c? If the mass of the residual nucleus is 3.9 times 10 to the power minus 25 kilograms, what is its kinetic energy in eV? We will consider that the momentum of the electron is directed along the y-axis and the momentum of the antineutrino is directed along the x-axis, and then you can calculate the tangent of the um, recoil linear momentum of the nucleus as simply being the magnitude of the electron's momentum over the magnitude of the antineutrino's momentum. And given the numerical values, this is just square root of 3. And as such, the angle phi is pi over 3, but the momentum itself is directed in the negative direction on both the x and the y axes. So for this angle, but it's going, it's not going like this. If you have a coordinate system here, x and y, let's say it's not going that way, but it's going this way. In any case, to calculate its magnitude, we simply use once again, over here we simply used basically the conservation of linear momentum for the vector quantity, and now we are using the conservation of its magnitude. So it's just its magnitude is just the square root of the sum of the squares of the two linear momenta, and the result is 2 MeV over c. And in order to calculate the kinetic energy, we know the definition of T in terms of V squared. We know the definition of linear momentum, so we can just solve this equation for V and replace it here, which gives the expression of T as P squared over 2M. We know the mass of the nucleus, and a kilogram, if converted in MeV over C squared, should have this numerical value. And if we bring it here, the end result should be that the kinetic energy is equal to 9.18 electron volts. So even if the nucleus carries a lot of momentum, that momentum is due to its mass. The kinetic energy itself is overall quite low. So due to its heavy mass, the nucleus recoils very little in comparison to the particles that are emitted. In any case, with the data provided by the problem, it appears that the reaction described should be the decay of protactinium 235 into uranium 235 plus an electron and plus an antineutrino. The observed half-life for this kind of beta decay is 24 minutes, and the half-life itself is entirely found in the beta decay channel, so this nucleus doesn't have any other observed decay modes, but the reaction energy itself is seen to be equal with 1.368 MeV, so it doesn't really add up with the momenta that are given in the problem, and I think that this is due to them wanting to have a simple geometrical result that would allow you to calculate the angle in a simple way. So that is why they didn't use the actual value of the reaction energy. In any case, the next problem involves two-dimensional oscillations. Its statement is the following. A Lagrangian for a particular physical system can be written with this expression for L prime, where A, B, and C are arbitrary constraints subjected to the condition B squared minus AC has to be equal to has to be different from zero. What are the equations of motion? Examine particularly the two cases A being equal to C being equal to zero and B being equal to zero with C being equal to minus A. What is the physical system described by the above Lagrangian? Show that the usual Lagrangian for the system as defined by equation 156 is related to L prime by a point transformation. What is the significance of the condition on the value B squared minus AC? The Lagrange equations are given here in their general form, and our generalized coordinates will be x and y. And if we do the very simple calculations, we obtain two equations which are describing, in short, the coupled oscillations in two directions. And you can see that if we take this set of values for A and C, then the equations become decoupled and we obtain two simple harmonic oscillators that are independent of each other. And the same works out if we take this set of values for our parameters. We once again obtain two independent oscillations. So, as mentioned, the system is a coupled harmonic oscillator in two dimensions. Particular choices of the coupling parameters can lead to independent vibrations. And if we consider the two equations here, uh, we can imagine a linear transformation of the coordinates of the type given here. So we can define a new set of variables, u and v, as functions of x and y using the parameters a, b, c. And if we use this transformation in the equations here, well, what we obtain is a set of two independent harmonic oscillators in the new variables. And these equations can be derived from a Lagrangian for a system having 2 degrees of freedom as described here. So we can always find a transformation that takes a coupled system and formally makes it look like a decoupled one, at least for this kind of situations. And the transformation itself in matrix form can be written as here. And you see that this matrix needs to be invertible because you always want to be able to express this equation either way. So either u and v as a function of x and y or the other way around. But the other way around requires for this matrix to be invertible, so for its determinant to be different from zero. But the condition that b squared is equal to with a times c implies precisely that the determinant is zero. As such, the transformation matrix is singular and the motion is degenerate. What you end up with is effectively a one-dimensional Lagrangian where you cannot really transform this coordinate in any meaningful way outside of rescaling it in one dimension. And the final problem for today involves a spherical pendulum. The statement is the following: obtain the Lagrange equations for a spherical pendulum that is a mass point suspended by a rigid weightless rod. This should be very simple and straightforward. Did I? Okay, yeah, I missed a slide. So these are the coordinates written in spherical components for a fixed length L. We calculate the time derivatives of these quantities and the kinetic energy follows immediately, and the potential energy is the one written here. It's written in such a way that when the pendulum is vertical and pointing up, the potential energy has its maximum value, and when it's vertical but pointing down, it has the minimal value because of the cosine here. So the Lagrangian follows very simply with the expression written at the bottom. And then it's a straightforward matter to calculate the partial derivatives and find the equations of motion, which are the boxed results. This is the equation for the angle theta, and this is the equation for the angle phi. And that is it for this set of problems. I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.